So we have a titration curve shown here on the right, which we can get, again, from UV-vis absorption spectroscopy. And we get a bunch of data points at different oxygen concentrations on the x-axis, and then we calculate on the y-axis what the ratio is of protein bound with O2 versus total protein. And this is the sort of plot we get, so it's called the ligand binding curve. And we see what's called saturation, so we're heading towards an asymptote of some sort, which is approaching an asymptote where theta is equal to 1. And then we have this curvature. So what is useful about this? What does this tell us? And so if you look at the equation on the top, so we have theta equals the concentration of the ligand over Kd plus the concentration of the ligand. And if you don't know how I arrived at this equation, please see the supplemental information on web courses for the explanation. And so we can fit these data, we can fit this equation rather, to these data points, which are shown here in black in the curve on the right-hand side. And so by fitting this equation, what we find is that a Kd, so remember this is the equilibrium dissociation constant, and that's expressed in units of molar, or some variation of molar, okay? And what the Kd tells us is that it gives us a quantitative means of saying how tightly does this bind. So if we vary the oxygen pressure in an experiment with reduced myoglobin, and we follow this curve, what we find is that when we fit this equation to this, what we get in the end is a P50, so Kd in this case, because we're using gas pressure and stuff, that's equal to P50. It's effectively the same unit, okay? So don't let that throw you off. But in this case, for myoglobin, it's 0.5 torr. And so that gives us a number which we can compare to the P50s for other gaseous ligands such as carbon monoxide, which we'll get to in a couple of lectures.